Hi class, let's go over how hydraulic brakes work and hydraulic lifts and things like that. So we'll use Pascal's principle in here, but let's just get the setup first. So we've got some, this is applicable in a lot of situations like tractors and with hydraulic parts on them where the bucket has to move and so forth. Brakes and cars have these hydraulic systems. The mechanics lift. You drive into the mechanic and they pump your car up to a high height so the mechanic can work on the underside. All those types of things are usually based on this principle of lifting with fluids. And so the idea is you build cylinders with pistons in them. And so this is a stiff-walled cylinder here, and then you snugly fit some part in the top that will not leak, or at least not leak very much at the sides, and it's free to slide up and down otherwise. So a good piston will slide very cleanly with very little friction. And so we're going to connect two of them, and they've got different sizes. So in cross section area, they're usually circles from the top view. So they are called cylinders for a pretty good reason. I've never seen a square one. I suppose you could build one, but I've never seen one. They probably don't work as well. And inside, so underneath this, we're going to put in some fluid, some water if you want to, but they usually put something even more incompressible than water in there. Brake fluid, I suppose, or transmission fluid, something, some kind of stuff in there. And so if you press down on this smaller cylinder, presumably this bigger piston up here would rise. So we'd have some action and reaction there. So let's draw a few force things. So we got our applied force this way, and we're expecting some output force that way. Well, heck, let's just list what we got going. So we're going to have forces. Let's just call them for cylinder number 1, and for cylinder number 2, let's call them force 1, force 2. They are heading different directions, we expect. There's a couple of cross-sectional areas. Let's just put subscripts on those guys too. So the top of this one, if you look at the cross-sectional area of this piston or that piston, they should be different. A2 should be big compared to A1 in this example. And we could have different pressures underneath too, because we're talking about fluid statics. So pressure in cylinder 1, pressure in cylinder 2. Well, how do you write pressure again? Pressures were written as force over area. So this isn't too hard so far. So changing to subscript 2, then we should have something like this. But now enter physics, and specifically Pascal's principle. So if we look at this fluid arrangement, they're connected here. So this is an enclosed, stiff-walled container filled with fluid. So Pascal's principle stated compactly is that inside that arrangement where you've got the machine and it's all enclosed, if you change pressure somewhere in there, that pressure change is communicated through the whole fluid. So in compact form, that just says that the pressure in cylinder 1 has to equal the pressure in cylinder 2 in such a circumstance. Well, that makes things kind of easy. So if we want to calculate forces, we just set those two equal. So P1 equal P2 becomes F1 over A1 is equal to F2 over A2. and that can easily be solved. If we want to know how much force is F2, say we're stomping on a brake pedal over here, we want to know how much force is being applied to the discs in our wheels over there, and we know the area, then what's left is we need to know the force. So solve for F2, which will be an F1 times the ratio A2 over A1. So this is pretty generic for these sorts of lifts, and so is this. So this is pretty easy math here. We just need to know the geometry of the two cylinders, and you need to know with what force you are stomping on the pedal, and then you get this F2. That can be big. So if we look at A2, that's the bigger cylinder here. That's bigger than the other one. So we're multiplying our force here. And if we really make a big cylinder over there, we can multiply our force by a lot. You can even cast this if you want to. If you remember mechanical advantage, that was our amplification of forces. And in this case, that would be the lifting, or the F2 over here over F1, and that's pretty easy to cross solve here. That's the ratio of the areas once again. So if you want a mechanical advantage instead, that's what it is. It's the ratio of the areas of the cylinders there. So is it odd that forces can be amplified? It might seem a little odd, but energy is conserved always. Momentum is conserved, but force is not a thing that's conserved, except for Newton's third law, where it's got an equal and opposite force attached to it. Force by itself is not really a quantity we expect to be conserved, so it can go wild, and this is one of those ways that it can go wild.